So today, our next topic of the previous video, after previous video, is Einstein's relationship between the various coefficients between spontaneous absorption, spontaneous emission, and stimulated emission. So, in the morning, in the previous two lectures of the lasers, we have discussed there are three processes: spontaneous absorption, spontaneous emission, and stimulated emission. But Einstein find out a relation what how the energy density and their coefficients they are correlated with each other. So um, let us discuss one by one. First of all, we will take the spontaneous absorption process. This is an incident photon. When it strikes here, let us say n1 is the number of atoms, n2 is the number of some number of atoms are there in the excited state. This is the initial state. We have assumed it. Now let us say some incident photon strike here. So the atoms gain energy and goes to the excited state. So this is the first process. This is called as the spontaneous absorption. And absorption occurs only when the energy carried by this should be equal to at least equal to E1 minus E2. So now according to this rate of spontaneous absorption is equal to, it depends upon N1 number of atoms in the ground state. If there is no atom, no absorption will take place. Second, it also depends upon the energy density, where rho mu is the energy density of the incident photon. If there is no photon, no absorption will be there. So the rate of absorption depend upon both the factors. So we will write it out n1 into rho mu, and we replace the constant as 1 proportionality b12, where b12 is called as a coefficient of absorption when the atoms after absorbing energy goes from state 1 to state 2. So that is the first part, and this one is the first part. And so the spontaneous absorption depends upon the number of atoms in the ground state as well as the energy density, and then this is the first part of the relation will be there. Then what happens in the after that, we have seen there is second process, that is the emission. Emission takes place in two ways. One is by spontaneous, another is by stimulated. Now spontaneous emission means the emission by itself. Stimulated means we enforce the emission to takes place from the outside. Now in the spontaneous emission, the excited state has very small time, that is 10 raised to minus 8 second. So the atoms which have got absorbed energy from the ground state goes to the excited state, they stay there for a very small period of time, that is 10 raised to minus 8 second. Now let us say n2 is the number of atoms in the excited state. Now after de-excitation they emit some energy and emission of photon. Now de-excitation depends only upon the number of atoms in the excited state. So the rate of spontaneous emission depends only on the number of atoms in the excited state, not any other factor, because it is without any energy density the atoms are coming out. So that means only N2 is there. So we will write out A21 into N2. A21 means atoms are coming from second state to the first state. So this is called as a spontaneous emission. Now third process, after that the third process will be there, that is called as a stimulated emission. Stimulated emission means there are metastable state is there, which is called as semi-stable state, and then the excited state is most unexcited, most unstable state, and so this is the main states which are being required. So now when the atoms gain energy and goes to the excited state, after that they come to the metastable state, and from the metastable state by the incident photon they bring back to the ground state. So during between the excited and the metastable state they emit radiation, that is called a non-radiative transition, which act like a heat radiations. Now when the atoms jump back to the ground state, the radiation will be emitted out. Now the rate of emission, stimulated emission, depends upon the number of atoms in the excited state, because only that atom will come here and then the stimulated emission occurs. And then it also depends upon energy density, because if there is no incident photon, no emission stimulation will occur, and hence no stimulated emission process takes place. So both of them depend upon these two factors. So we will write it here as B21 into N2 rho 1. B21 is because this level is very close to it, so we call it as a B21 only. Now at equilibrium what happens, rate of absorption is equal to rate of emission. Now rate of absorption, we have got the rate of absorption by the equation 1, n1 b12 n1 rho mu, and then the rate of spontaneous emission a21 n2, and then the third is b21 n2 rho mu. So we have put them, absorption is equal to emission, and then we calculate the factor, that is where the energy density is there, both the values are being taken to this side, and then find the value of energy density. So this is called as the equation A. Now this equation consists of A21 N2 upon B12 N1 minus B21 N2. Now we divide numerator and denominator by this factor. So after division, we get some particular part of the equation. So that particular part of the equation will be like this way. That is this one, A21 N2 upon B21 N2, this one and this one. Now we cancel out the common factors, so we will left behind with this part and this part. So that is B12 upon B21 N1 upon N2 minus 1. But Einstein has proved it thermodynamically that B12 is equal to B21. So that is B21 or B12 is equal to 1. So that means we will put the value here as 1. Now, to get this equation in the standard form, we use the formula given by Boltzmann, which has stated that the atoms in the ground state to the number of atoms in the excited state, they are correlated by this relation E raised to h mu by kBt. So now we correlate this, substitute this value over here, and we got this equation in new form. Call this as equation 1. Now again then, to get the value of energy density, we compare it with the Planck, who is given by black body radiation. The energy density is given by this relation. According to Planck, the energy density of any radiation is given by 8 pi h mu cube by c cube into 1 by e raised to h mu by kBt minus 1. So this relation is there. Now the energy density relation is given from the Einstein. Find the coefficients is by this equation, that is by equation 1 and equation 2. Now we will compare them, and then after comparing we got the value of A21 upon B21 is equal to 8 pi h mu cube over c cube, or where 8 constant, pi is constant, h is constant, c cube is constant, so that means it depends upon the vacancy cube. Or we, since we have know that B21 already equal to B12 according to this relation, so we can put here A21 upon B12 is equal to 8 pi h mu cube over c cube. That means this ratio depend upon the vacancy cube. So that means this relation says that the spontaneous absorption and stimulated emission depend upon the ratio of the vacancy. Spontaneous emission and spontaneous absorption again depend upon the vacancy cube. Now what are the conditions required for the large amplification to take place? So this is the final relation between the various Einstein coefficient. Now using this relation we can able to find out the condition required for the amplification. Now the condition required for the amplification will, let us say, we know that we find the ratio of stimulated emission upon spontaneous emission as B21 upon A21 into rho mu. Similarly, we can write stimulated emission upon spontaneous absorption as equal to this one, or N2 by N1, because B21 is equal to B12. So now these are the two conditions which are required for the amplification. Now to make stimulated emission energy to be larger, stimulated emission to be larger, this value should be more. That means it depends upon the energy density. This equation shows that if you want to make more amplification, the energy density should have a larger value. Then second part, which is saying that to N2 by N1, again stimulated emission to be more, because laser action is going to take place because of the stimulated emission process. For this process to take place, N2 by N1 should be much greater than 1. That means N2 by N1 is greater than 1. If the N2 is less than N1, no stimulated emission will take place, or dominance of stimulated emission will be less, so that will be no proper laser action will take place. So N2 is much greater than N1 means number of atoms in the excited state is much greater than number of atoms in the ground state. So that process is called as a population inversion. Now what is population inversion? Let us see. Now population inversion is again a process which is required for the laser to take place. That is a population inversion, that we by some method we excite the atoms in the excited state in such a way that the number of atoms in the excited or in the metastable state should be more than the number of atoms in the ground state, because stimulation will occur only where if the number of atoms are available in the metastable state. If there is no availability of the atoms in the metastable state, no stimulated emission takes place. So population inversion is the essential process which is required for the laser action to take place. So this was all about the second part of the today's lecture. Thank you.